I'm Weichen Xie. This is a joint work with Ada, Chris, and Tino, and it's based on the archive paper we have. So spatial search, first, it's a search problem. So search problem is something like this. We have a data storing in a physical like a box here, and the box has an address. And for simplicity, we can just assign a number for the address. So we call it 0. And in fact, there are a lot of data we have. And so we have, in this example, we have 6 different boxes and storing different data. And the edges means we can go from one physical location to the other location. Okay. And we have, and to find the target, so we have another piece of box to find a target. So it's storing with a target, and it will compare with the data to check whether the data is inside a specific box or not. Okay, and typically this one is a black box, so we cannot open it up. So there's nothing I cannot see what is the target, and I can only use it to check box by box. Okay, and if this black box, we call it an oracle, and it takes the address as an input, and it outputs yes or no, or 0 or 1 if it depending on whether this data is the target or not. Okay, so we can check the box one by one. So in here we first check box number 3, and then box number 4, and box number 0, and so on and so forth. As long as they have a connection, then we can move from one box to the other one. Okay, and classically we got to check this box. In the worst case, we got to check the box one by one. So we got to check it. In the worst case, we got to check it n times or 6 times here. And Grover says it can be faster. Be done by quantum computing. Okay, so to make our problem simpler, we abstract this into a graph. So every vertex representing the box we have, and the edges are still the edges that describing the connection between the boxes. And the self loop here representing the oracle. So there is somebody else, we have no idea who, but somebody puts a self loop on one of the vertex, and we call that target vertex W. And our job is to run the quantum evolution and hoping all the amplitudes would concentrate on this target vertex. Okay, and this method it's called analog by Farley and Goodman. They're proposing in the 1998, and they construct a Hamiltonian line H equals to S dagger plus W dagger, and the S is all one superposition over all the vertices. W dagger, that is the oracle. Okay, and it evolved the whole system under the Schrödinger equation. So we will get immediate 2 results. First, this W can be the target vertex can be perfectly fine in time power 2 times square root n. Okay, so we can find this target vertex with probability 1. And the other result would be this target actually cannot be found in time earlier than square root n. So that's saying this is the optimal time. Quantum power enables a quadratic speed up over the classical algorithms, and this quadratic speed up is achievable also by using this algorithm. So this is called analog because it's a continuous time version of the Grover search. Okay, and this SS dagger is the Grover coin. So and the WW dagger is the oracle. Now we have a comparison here. So for the analog, our initial state is the O1 vector because we have no idea which vertex is the target vertex. So we're starting with a O1 vector to representing a uniform uniform distribution over all the vertices. And then the Hamiltonian would be the S dagger plus WW dagger. That actually it's the SS dagger that it actually is the adjacency matrix of a complete graph. So that actually says the Grover search it's a well in this continuous time version, it's a continuous time quantum walk over the complete graph. This is the SS dagger, means the adjacency of matrix of the complete graph. And this WW dagger, it's we got to put a self loop on one of the vertex. And evolution, it's a Schrodinger evolution, so we can easily solve it, and it becomes e to the minus I ht times the starting state phi 0. And the fidelity, that is the actually it's the probability for finding the target state. So it's just the inner product with the W and the state vector, and then we take the norm square to calculate the probability. So for spatial search, things are similar, but it got generalization. It got generalized because the initial state here we got instead of using the all-one vector, we're actually using the principal eigenvector. So in a case where the graph is a vertex transitive, the principal eigenvector is exactly the all-one state, and this is the principal eigenvector would give us would make our life easier because we eventually got to use the spatial decomposition to compute the probabilities. So this can be convenient. And the Hamiltonian for the spatial search would be this gamma times the adjacency matrix of the underlying graph and plus WW dagger. So there's the self loop. The gamma here, it's also coming from the SS dagger because if we go back to the previous slides here, we can see this SS dagger, it's 1 over n times all1. So that is actually it's the adjacency matrix multiplied by a constant, multiplied by a factor. So that factor here can be generalized to be a gamma. We have no idea what is this gamma yet, but we will keep it here in the model. And then the evolution is just a Schrodinger evolution, so we can solve it, and it has the formula e to the minus ith multiplied by the initial state, and the fidelity is still the probability for finding the target state. So this is the state vector, and actually we can also do that in terms of the density matrix. So our initial state would be the density matrix, so it would be the E1. E1 is the principal eigenprojector, and Hamiltonian is still the same. We do not change the Hamiltonian, but evolution, because we're using density matrix, so we got to conjugate by the unitary evolution on both sides of the density matrix. So we got the e to the minus ith times the initial density matrix multiplied by e to the ith. The advantage by using the density matrix is because we don't need to calculate the we don't need to worry about the local the global phase. So this give me some convenience to compute. And this finally we have the fidelity. That's the trace of WW dagger multiplied by the density matrix. That is exactly the probability for finding the target vertex. Okay. So by doing this, the first result we can have is there will be a time lower bound. This is a direct generalization of the analog result. So there would be if the fidelity is a constant, then a time tau for some gamma, then the time must be at least 1 over the norm of E1 multiplied by H. So that is E1 multiplied by H. That is you can view it as the projection, projecting the target vertex, target vector to the principal eigen subspace. So this is the shadow. We call it the shadow. We will use epsilon to denote this term. Okay, so for the spatial search, now I can formally define the spatial search here. We let the G to be a kinetic graph with the normalized adjacency matrix. So to normalize the adjacency matrix, it's easy because we can subtract the smallest eigenvalue and then divide by the largest eigenvalue minus the smallest eigenvalue to make it to make all the eigenvalues up lying between 0 and 1. So this is easy. This can be done. And we have immediately we have this spatial decomposition. So A equals to the sum of theta r times ER. ER is the eigenprojector, and theta r is the eigenvalue. Like I said, they are ordering in a decreased order, and they're all discrete. Well, in terms of the spatial decomposition, we can just label all the discrete eigenvalues. So there are totally D of them. And the principal eigenvalue is 1, and the smallest one can be 0, can be bigger than 0. It doesn't matter. And we also call the shadow epsilon. That is the E1 operator W projecting on the principal eigen subspace. So that's the epsilon, and it's not 0, but it's a subconstant. Okay, so it's a small O(n) of 1. That means it's asymptotically it would go to 0. It's not even a constant for each W. So here in the previous talks, there says the W it should be known in order to find the W or to run this algorithm, the W should be known in previous. But here we actually can focus on the graph that's vertex transitive, so it doesn't matter where W is. The amplitudes are always the same. The epsilon ones are always the same. So it's not depending on whether we know the target or not. Okay. So and the starting state we choose the principal eigenvector, or in terms of the density matrix we choose the principal eigenprojector, and then we say Gn is gamma covariant if for some time the time should be 1 over epsilon of order 1 over epsilon 1, and the state driven by the Hamiltonian would get a constant fidelity. So because we focus on the optimal search, so we want to force the time to be the best ever, the best time we can have, and we actually get to sacrifice for the fidelity here. It may not be probability 1, but as long as it's a constant, we are fine, because we can repeat the whole process by a constant amount of time. So this is a gamma covariant, and we have to choose the gamma here. and we call a Gn a covariant if it's gamma covariant for some gamma. Okay, so overall we just call it a covariant here. So there are many known examples for the covariant graphs, like the complete graph that is given by the Théorie and Goodman in 1998. That's the analogue. And hypercube by Charles in 2002. Complete bipartite graphs and strongly regular graphs by German et al. In 2014. So all these graphs are, well, I typically choose this graph because these graphs are all vertex transitive. So you don't need to know where is the vertex, where is the target. And there are also other graphs like the barbell, we call it the bridge complete graph. We got other graphs that's not a vertex transitive, but still it will if we know the target, then we can find it in the optimal time. Okay. Oops. So there are a long-standing open problem here. We want to know what kind of graph it's covariant. So we want to have a clean characterization for the graphs. And there was this one. First, Chakraborty et al. In 2016, they found a constant spatial gap implies the covariant graph. And later in 2020, they make it better. It finds a partial characterization for the covariant. And what we are doing is we actually found a necessary condition for the covariant. Okay, so if we look at the spectrum of the gamma A plus W dagger, that is the Hamiltonian of the search, spatial search. And we got this gamma here. This is the largest eigenvalue of gamma times A. And because we plus WW dagger, that is a random perturbation. So all the eigenvalues would be lying, would have a shifting to the right. So the largest perturbed eigenvalue would be, we call it zeta1. It would be on the right of the gamma. So we actually can say if this the gap in between zeta1 and gamma, we call it delta plus. That is the gap. If it's asymptotically the same as epsilon 1, then this is a necessary condition for the covariance. So this is the first one. And the second one is look at this gamma theta 2. This is the second largest eigenvalue of the underlying graph. And again, because the random perturbation, so the perturbed eigenvalue will be on the right, and actually it would be in between gamma theta 2 and gamma. So it will lie in between here. And the gap gamma in between gamma and zeta 2, we call it the delta minus, and this should be asymptotically the same as epsilon 1. That covariance implies this one. And of course, this is not always the case because this gamma theta 2 can be so close to the principal value. So in that case, there should be somebody else should line up with the epsilon 1. So we said there is a zeta m, and the gap between gamma and zeta m should line up with epsilon 1 for some m in the case where the second eigenvalue are so close to the principal one. So that is a necessary condition. That's in general, it's saying there is a perturbation on the eigenvalues, and all the eigenvalues would be perturbed to the right, and it has an interlacing to each other. And we focus on the first gap here. This is the we call it delta plus, and to the left there should be somebody else that should line up with this gap to make the kind of the same gap. This is what this necessary condition says. Okay, so for the if we can pose this condition here, epsilon is much less than square root of S1 times 1 minus theta 2. That is the spatial gap. This condition would force this the second largest eigenvalue would be far away from the S1, and the perturbed eigenvalue would have a chance to line up with the first spatial gap. And in that case, we say the graph is S1 covariant if S2 over S1 is S2 over S1 square is a constant, asymptotically is a constant. Okay, that is the same result as Chakraborty et al. And our condition is easier compared to their results. Okay, and here the S it's called the search parameter, and it's defined by this sk equals to the sum. We get rid of the principal eigenvalue, and then it sum over all the ER all the shadows and dividing by the spatial gaps for k equals to 1, 2 all the way. But here we only focus on k equals to 1 and 2. That's the general necessary condition and a partial capitalization for the covariance. And actually, we can do better if we focus on gamma. If we compare gamma with the S1, that's the mystery number here. We can get two more necessary conditions. The first one is if the epsilon 1 times S1 is much less than gamma minus S1, then the H it's not covariant. So the underlying graph will not be covariant under this case. So this is saying if we choose the gamma to be too big compared to S1, it's so big, and the H and the spatial search will not work. It's because we kind of remember the gamma, it's gamma, the Hamiltonian equals to gamma times A plus WW dagger. So if the gamma is too big, then the self loop, it's kind of, it can be ignored. In some sense, it can be ignored. So it's just not putting the self loop. So of course, you cannot find the target. So that is the first one. And the second one is when the gamma is around S1. This one is a boundary case, so we have more assumptions here. We have to assume all the shadows W projecting on different eigen subspace, and this shadow should be bounded by the principal shadow. So it should be less than C, a constant multiplied by epsilon 1. And also, we also need to define this. It is set I alpha. It equals to R. It's counting the number R. Actually, it's counting the eigenvalue that satisfy how many eigenvalues that was satisfying this alpha epsilon 1 to the power alpha multiplied by 1 minus delta R to the power minus 1, and it got to bigger than R gamma. So this set is counting how many eigenvalues would satisfy this condition. If the gamma is around S1 and this set is bigger or equal to 2 times a C squared, so this is some constant for alpha in between 1 and 2, then this H will not be a gamma covariant. So but like I said, this is a boundary case, so we got to get our hands dirty, but eventually we still got this condition here. So why these two are useful? Because we can prove the cycles will not be a covariant. And in the previous talk, they say the cycle, they kind of proving the cycle it's not covariant by using the Lie-Wilkinson bound, and that's saying the time. The time for finding the target, it would be bigger than square root n, and here we actually have a more precise characterization for the cycles. It actually turns out for the cycle, no matter how big the self loop weight you put, or no matter how big the gamma is, you will never find the target state or target vertex. So for the cycle, we got to calculate the normalized eigenvalues. So these are the eigenvalues. Theta r equals to 1/2 plus multiplied by 1 plus cosine 2 pi r minus 1 over n. So this is just a so for the cycle, if we are not doing normalization, we will get the cosine 2 pi r minus 1 over n. And by subtracting the smallest eigenvalue, that is the -1, and we're dividing by the eigenvalue gap. So the largest one minus the smallest eigenvalue, that is the 2 here. So we will get this formula. We can compare the gaps in between the eigenvalues. So this delta R is defined by the principal eigenvalue minus the rth eigenvalue. So it's 1 minus theta r, and it's asymptotically the same as r squared over n squared for small r. Okay, because this r is moving from 1, 2, 3 all the way to n. So if it's asymptotically smaller, much smaller than n, then this r is a constant, and it would, by using the cosine, it's asymptotically equals to 1 minus cosine squared over 2, then we can get this result here. And epsilon, that is the shadow, because the graph, the cycle graph is a vertex sensitive graph. So it actually, all the shadows would be 1 over square root n. That is the principal eigenvalue, principal eigenvector, the terms of the principal eigenvector. It's 1 over square root n here. So immediately we can compute the S1, because the S1 equals to 1 over S1 equals to the sum of the shadow square over the eigenvalue gaps. So we can compute things like this, and by doing approximation, we will get this term. It's actually asymptotically the same as n. So it's of order. So we can see this by using this informations, we can see our partial characterization will not work because it's because the epsilon is not much less than where is the this one, because epsilon 1 is not much less than square root of S1 times the delta 2. So we cannot use this theorem to prove cycles are not working. Instead, we got to use the two theorems, the two necessary conditions we have. So let's prove it. The first case is when this gamma equals to S1 plus the omega n of square root n. So this omega means this term is of order at least square root of n. Okay, so that's saying your gamma actually is much bigger than the S1 because it's S1 plus this term. And we can check the epsilon S1, it's of order square root of n, and the gamma minus S1 is of order omega of square root n. So this is at least square root n, but of course it would be bigger than of order square root n. So the first necessary condition will apply. So this is saying when your gamma is too big, the spatial search will not work on the cycle. And when the gamma is around S1, this time we got to check how many eigenvalues would lie in the set I alpha, and we just need to check this condition here. It's n to the minus alpha over 2 multiplied by n squared. This is bigger than gamma. This is actually what I'm checking here is this one. Let me go back to. Okay, it's checking this one here. So the gamma is already given. By assumption, it's around S1. So this is around n of order n. And this epsilon 1 to the alpha, that is epsilon 1 is 1 over square root n. So it's n to the minus 1/2 multiplied by alpha. And then this delta 2, it's this delta 2 is a 1 over n squared. And you have another minus here. So it becomes 2 minus alpha over 2. Okay, go back to here. So we got this one here. 2 minus alpha over 2, and compare with n, of course, it would be asymptotically bigger than n. That means there are a lot of eigenvalues would lying inside the set I alpha. So that means the number of elements of I alpha would be bigger than 2, at least bigger than 2. And this bigger than 2 will allows me to use the necessary condition to kill it. So that's saying when alpha is around S1, the cycle is still not working. The last case is when the gamma is smaller than order n. So it's big O n of n. In this case, we don't have any theorems, so we have to prove it by repeating the previous arguments. So we need to show the delta plus it's much less than epsilon 1. This is our proof technique. We actually using the general necessary condition to prove this is not working. In a general condition, delta plus should asymptotically be the same as epsilon 1, and we're proving if it's smaller, then we can kill it. Okay, so to prove this, we actually suffice to show delta plus it's of order epsilon 1 to the alpha, to the power of alpha, and for some alpha in between 1 and 2. So we are not satisfying. Well, it would be harder to prove to get alpha equals to 1. So I just make it bigger. So alpha is in between 1 and 2. And if delta plus is smaller than alpha to the power epsilon to the alpha, then of course it would be smaller than epsilon 1 to the power 1. Okay, so this is the condition here. And to show this, we just need to check the characteristic polynomial by plugging in this number here. So we check the characteristic polynomial of h by plugging gamma plus epsilon 1 to the power alpha, and we want to prove it is bigger than 0, then we can say this is delta plus would be smaller than epsilon 1 to the power alpha. Okay, and open up the characteristic polynomial, we will get this ugly formula here. So eventually it turns out to be one bigger, we want to prove one is bigger than this summation. And this summation we can separate into two parts, the principal term and the others. Okay, so it becomes epsilon 1 to the power 2 minus alpha plus 1 over gamma times the other terms, summing over the other terms. So we focus on the second term, the second summation. In fact, we can separate it into two parts because we are comparing the delta R and the epsilon 1 to the alpha over gamma. So we can separate it into two parts here based on whether delta is smaller or delta is bigger. Okay, and if delta is smaller, I can make the whole term bigger by doubling the delta here. Okay, and if delta is bigger, then I can just get rid of the epsilon 1 to the alpha over gamma, just ignore it to make the whole term bigger. Okay, and so these two terms are only off by a half. So I plus the half of I pass the first term and then minus the first term again, and I would make the S1 back here because I can get rid of the 2 here, and I got to minus the first term over 2. So it becomes S1 minus 1/2 of this term here. This term is exactly the same as the first term. So it suffices to prove if I plug in the upper bound to this inequality, and if it still satisfies, then I can prove I can say the characteristic polynomial is bigger than 0. Okay, so it suffices to show 1/2 of the first term is bigger than gamma times epsilon 1 to the power 2 minus alpha plus S1 minus gamma. And we focus on the right hand side. Actually, every term we check every term. This is gamma, it's of order at most n, and epsilon 1 it's of order 1 over minus 1/2. So totally this first term it's at most order n, and S1 it's by computation S1 is of order n, and the gamma by assumption this is at most of order n. So the right hand side, these 3 terms totally it's at most of order n. Okay, and now we only need to show the left hand side, this ugly summation, it would be order n. Then we can show this inequality. Okay, this can be done by checking this delta gamma, delta R equals to 1 minus theta R, and it's when R is small, it's of order R squared over n squared, and this is much less than epsilon 1 to the alpha over gamma. Okay, so what does it mean? It means I can just use finite terms of R here and replace this summation. So it would be this summation would be bigger or equal to for summing the R from 2 to B to some number, constant number, and epsilon R squared over delta R. And this thing would be of order n to the minus 1 over R squared times n to the power minus 2. And this summation is of order at least n. Okay, so we show the left-hand side is at least of order n, and the right-hand side is at most of order n. So this inequality would satisfy, and that finished the proof because this inequality implies the characteristic polynomial is bigger than 0, and that's implying this delta plus it's of order at most epsilon 1 to the power alpha, and that's saying delta plus it's much smaller than epsilon 1, and that and then we use the general necessary condition to kill this situation. So that's saying the when your gamma is small, the spatial search still not working on the graph, not working on the cycle. So so as we can see here, I kind of conducting two simulations on MATLAB, and you can see over the time steps, the time is moving here, and the amplitudes are barely move. So that means there's no way you can concentrate on the target vertex. Okay, no matter how long you wait, it will never concentrate to the target vertex. It's not just saying it will be slow, it's actually saying no matter how long you wait, it will never work. There are some remaining questions we have. So the first thing is the S1. We have no idea what's the combinatorial meaning for S1 or the graph theory meaning for this S1. So they said it's a search parameter, but still we have no good explanation for what's happening here. And the second one is the covariance graphs. From all the example I check, or as far as I know, the S1 it's always at most a constant. Usually it would, but the thing is, we have no idea whether we can see a covariance graph with S1 is at least a constant. So that's saying the S1 would grows to infinity as long as your n goes to infinity. So, and the other thing is we have no idea whether if there are any other necessary conditions, because in this case we're lucky, we're showing the cycle it's not working for all time, and obviously we cannot characterize how for example, we can characterize the 2D lattices, because it's that 2D lattices is saying you got to wait a longer time. It's not the optimal time, but you got to wait longer, and eventually the amplitude will concentrate on the target vertex, and this is out of the scope of our result. And then next thing is we don't know whether covariance can be fully determined by the spectrum of the underlying graph. This necessary how necessary would be for the partial characterization. So we have a result saying epsilon 1, if epsilon 1 is much less than square root of S1 times delta 2, then we have a if condition for the spatial search, but we don't know whether we can push this to a largest set. And the last thing is how when does the covariance implying the periodicity. So as far as I know, while proving the covariance, we actually focus on a two-dimensional subspace. So it's saying, this is saying, it's something similar to the Grover search. So you have, you focus on the largest eigen subspace and the second largest eigen subspace. And then there is by focus on these two subspace, it will trap the amplitude of the whole evolution, and the other space are kind of not playing. So in this case, the covariance kind of implying the periodicity, but we don't know whether we can do it in the three-dimensional subspace or higher dimensional. So, and this is pretty much all I have, and thank you very much.
Are there any questions for Sam? I have a question. Do you know how, have a sense of how common these necessary conditions are that you had?
So, like I said, we are very, very lucky, because these necessary conditions are all assuming there's no time you can reach the target state. So we are very lucky to prove the cycle is not working. But when when it will concentrate to the target vertex, but with a longer time, we have no characterization for these things. So that's why I'm asking if there are any other necessary conditions. Yeah.
If there are no more questions, let's thank Sam again.